characterization using destructive testing for a race plane that I am building. And I feel a little bit like a pariah among lighter people to be talking about something with an engine, but bear with me, I think you'll find it interesting. Yes, I have a very bad aspect ratio. So I'm just going to give a quick self-introduction about myself. I'll talk about the goals of the SR-1 project, a brief introduction of materials testing, a quick rundown of the tests that I've done for the race plane, and then I'll be open to some Q&A. I have a bunch of test coupons and materials that I have tested over the last 3 or 4 years. They're all up here on this desk, so feel free to take a look at them if you like. I'll probably pass some of them around right now just because they're in boxes and easy to keep together. Other stuff, like I have a bunch of coupons. If you want to look at those, come on up, because otherwise they're just going to end up all over the room. Alright, so although I am talking about a powered aircraft, I did begin with gliders. I built a Gentle Lady RC model. That was the first RC model I ever built. And for any of you who are in RC, it's a very nice flying glider trainer. And then in college, I did the SAE Aero Design Heavy Lift Competition. Just basically a college competition to build an airplane with a limited wing area to lift as much weight as possible. In 2011, I finally had money and time to build my dream project, which is an RV. It's sitting outside right now. And then in 2015, I started on my second airplane, which is the race plane that I'm going to be talking about right now. Kind of between 2013 and 2015, I worked at Bob Kuykendall's shop for probably 2 months on and off because I didn't know anything about composites. I had built an aluminum airplane, but composites is totally different. So I learned a lot with Bob. He's a super cool guy. If you ever have a chance to do an aqua fleet, I highly recommend it. And then I also worked with Paolo. I probably worked with him, I don't know, 5 or 6 months over the last 4 years on various projects. So that was also a really good learning experience. I write for Kit Planes, and I've also done some articles for Air and Space and Red Bull as well. And finally, another thing that I do, again, completely irrelevant to glider stuff, is I install wireless torque meters on race plane engines. So most of the Red Bull race planes have wireless torque meter that I didn't design it, but I do the torque meter installation. I'm not an engineer, I'm self-trained. My degree is in Japanese. So this is a video of the RV that I built, and just a quick, it's set to Major Tom, and we all like that song. So the name of my airplane is Banana Puddin', and so this is a short video. It has Japanese subtitles because I lived in Japan for 12 years and all of my friends wanted to follow along.
Standing there alone, the ship is waiting, all systems are go. Are you sure? Control is not convinced, but the computer has the evidence. No need to avoid. The countdown starts. Watching at a trance, the crew is certain, nothing left to chance. All is working, trying to relax. Up in the capsule, sent me up a dream. Jokes Major Tom. The count goes on.
If you've ever landed out at Smith Valley, you know this runway. Mono Lake.
in orbit, stabilizers up, running perfect, starting to collect requested data. What will it affect when all is done? Things Major Tom. Back at ground control, there is a problem. Go to rocket school. Mike responds. Hello, Major Tom. Are you receiving? Turn the fences on. We're standing by. There's no reply. 4, 3, 2, 1. Below us, drifting, falling, floating, weightless, calling, calling home. Across the stratosphere, a final message. Give my wife my love, then nothing more. Father moved the ship.
I think in the Aviator, Howard Hughes talks about how important it is to have clouds when you're doing airplane scenes, and he's really right.
This is my home. I'm coming home. And below us, drifting, falling, floating, weightless, coming home. And below us, drifting, falling, floating, weightless, coming home. And below us, drifting, falling, floating, weightless,
I'm going to stop that there. So, as Paolo said, why do we do these things? I'm not really sure. We're probably a little bit crazy. But the SR-1 project is an attempt to break a speed record in the 300 kilogram category. That was Paolo's plane. He showed you that on one of his early slides. That's the plane that he built as his senior design project, which is super impressive that someone who had never built an airplane before, as a 22-year-old, built something that ended up setting a world record. So Paolo's airplane currently holds the record at 224 miles an hour. He set that with an 80 horsepower Jabiru engine. There was an Austrian fellow owned the record in between Paolo and Mike Arnold, but Mike Arnold's plane is also pretty well known. I think you all know who Bruce Carmichael is. He wrote a good article in Contact magazine that did a drag assessment of the AR-5. I actually spoke with Bruce like 4 or 5 years ago when I was starting this project. I called him up and I said, what do you think about a person doing a suction stabilized laminar wing? Because that was kind of his specialty. And he said, yeah, it's doable, but it'd be a lot of work. So the wing on the SR-1 is not suction stabilized. Maybe the next one. All right, so how to go faster than Paolo? Well, there's 2 ways. Either the airplane has to have less drag or it needs more power, or both. Less drag is basically accomplished in this airplane by being smaller. It has about 75% of the wetted area of Paolo's airplane. So by virtue of simply being smaller, it's going to have less drag. The second way to go faster is to have more power. Paolo, for various reasons, was limited to using an 80 horsepower Jabiru. I would like to have a larger engine, but bigger equals more power, but it also means heavier. So one of the big challenges with this project is to keep everything that's not an engine, i.e. all of the airframe, should be absolutely as light as possible. And the pilot will also be as light as possible. I'm going to try to find a very small person to be the pilot. And a lot of the focus of this project is getting things absolutely as light as possible. And so that leads into materials testing, materials processes, how you do layups, etc. And then also parts design, testing parts to make sure that they're as strong as necessary, but hopefully not anything more than you need. So why would you do testing? There's a number of reasons that we do tests. For example, metal alloys are really well known, and there's a limited number of them. They're well characterized. And so in comparison, composites, there's almost an unlimited number of resins that we can get, pre-pregs, wet layups. There's a vast number of fabrics. Paolo talked a little bit about some of the specialty fabrics that he was able to use in the Nixus project, and different ways of processing these things. Are you doing a wet layup? Are you doing autoclave? What kind of post-curing are you doing? So all of those things are they end up being very specific to each project. And if you can do some materials testing during the project or before the project, then again, that helps you optimize the use of your materials. The second reason to do testing is that a lot of data is proprietary. And companies like Boeing, etc., will do a test, but they spend millions of dollars characterizing these materials, and they don't share it. And what they're testing is also not really relevant to somebody building a really small airplane. So there is some data, and Paolo also mentioned that the tests that they did were done, I guess, was that done with public money, Paolo, so that it's part of Agate? Yeah, so that's on the NIAR Agate website. But a lot of those test coupons are relatively thick. They typically do 12 plies. It's about 1/10 of an inch thick. There's reasons for doing that because it makes it easier to do your tests, but we rarely use that many layers in a small GA airplane or a drone or whatever. I mean, typically we use 2 or 3 layers, and sometimes you could get away with 1 layer if it wasn't for gauge thickness factors, i.e., you want to be able to not have somebody put their finger through something, and if you only have a single layer, it might be strong enough from a structural point of view, but you're going to have really bad hanger rash issues. So once you start doing structures that are only using a few layers of carbon or fiberglass, you get a big knockdown. And so a knockdown is, they might say that a material has 100,000 pounds compression strength, but in fact, if that's a very thin material, your compression strength might be much lower. It might only be 20 or 30,000 pounds. And that's due to buckling issues and some other factors that are related to knockdown. For me, as the person who's making these things and then testing them and breaking them, it's not, one of the major benefits is that it's not just getting quantitative information from these tests, but I also get like a qualitative and an intuitive sense of how things fail. And I feel like that's a really important part of doing the testing is just seeing how things feel or how they fail and getting a feel for the materials that I'm using. Another reason is that these results are real in a sense because, again, it's just a test and we might only be looking at one parameter. But it's a different kind of information than what you would get if you do, say, a finite element analysis, which is really the results that you get from a computer model is kind of the GIGO, garbage in, garbage out. It's really dependent on the skill of the modeler, what kind of software you're using. And if someone knows what they're doing, they can get great results. But I'm not trained in FEA. I mean, maybe the next project I'll learn that. But So for me, getting real results that I could then apply to the project was really useful. And then finally, the last reason that I have on here, and I'm sure people could come up with more, but doing testing allows me to validate my fabrication processes. So I'll give you an example. When I first started this, people said you need to mix up micro, which is epoxy and micro balloons, into a thin paste and put that on foam core before you put your fabric on. And I said, why? Or how do you know this? I don't believe anything, so these are questions I often ask. Paolo wishes that I would believe more, but I often don't, and I say, prove it to me. So one of the early tests that I did was to make up a bunch of coupons, and some of them are here. And I did coupons where I just I put the foam core into the laminate perfectly dry. I did ones where I rolled the foam core with a porcupine roller. I don't know if you know what one of those is, but it puts a bunch of little holes in the foam core so that the resin can grab onto it. I did porcupine roller with micro. I did just straight micro. And so I did all of these, and I was able to determine there's absolutely no reason to put micro on foam core. And there's also no reason to do porcupine roller, at least the way that I make it. Someone else might do this, might do their processes different and get different results, but I'm the one building the airplane, and what works for me is just dry core, no porcupine rolling, and that also ends up being the lightest way of making a sandwich coupon. So I have used 3 types of testing on the SR-1 project so far. The first is scale models. The second is ASTM coupons. So by a coupon, we just mean something like this, where it's a prescribed shape and composition, and then we have a particular way of testing it. And when I say a particular way of testing it, ASTM is, I should know what this stands for, American Society of Testing and Materials or something. But they have basically a recipe for doing a test. It's very straightforward. It's not super technical. It just says, use this test if you're trying to find out a certain type of information. This is what your coupon should look like. This is what the testing machine should look like. Here's how you should conduct the test. Here's what failure modes you might see. They're usually about 8 to 10 pages long, and we try to stick to this as much as possible. And the reason for having standards is so that if I do a test and you do a test, we can compare our results. And then the third type of testing that I do is actual parts and assemblies. So I sent around a box. Who's got the box right now with the cables in it? And it's disappeared. That's okay. I'll get it back. Oh, there it is. So when that box comes around, you'll see a bunch of steel cables as well as some cables with Dyneema. And those are a test for the rudder cable system in the airplane. Dyneema is as strong as steel, and I thought, well, it's a hell of a lot lighter. This would be a great thing to use in the airplane, but as a actuating assembly, nobody's ever really done it that I know of, and I need to make sure that this is safe. And so I basically made a model of how I would actuate my rudder cables using Dyneema, and then I also had somebody just make up some standard 1/8" steel rudder cables and tested those, and to the point where I'm satisfied that I can make Dyneema rudder cables that are as strong or stronger than steel rudder cables, and they weigh 7 times less. So in this particular project, the Dyneema cables will weigh about 2.5 ounces, and a steel cable assembly would weigh about 15 ounces. And so it's about a 13-ounce difference, which in this airplane is huge, because the airframe weight will be maybe like 250 pounds without the engine. So a 1/2 pound or 1 pound is a lot. For the scale model testing, I set the little stubby wing around. When I worked with Bob Kuykendall, he uses the pultruded carbon fiber rods, if any of you are familiar with that, same as Marsky does that with the Monarch spars. The numbers that are published for those protruded rods are really high, and I wanted to be able to validate that strength because it's probably twice the strength that you would get with a hand laid up carbon spar. And so if I'm going to use half as much material, I want to make sure that it really is that strong. So I read Stan Hall has an article on scale model testing. I kind of used that, and I made a quarter scale spar that mimicked what I was doing in the SR-1. And then I went ahead and tested it, and it broke very close to the published numbers for compressive strength of protruded rods. So that was an example of where a scale model validated the numbers that I was using to design the actual spar. And let's see here. So this is that little stubby wing that's going around. This is it loaded with, I think there's about 600 pounds on here when it finally goes. And this is not the most beautiful load distribution, but basically just trying to validate that it's pretty, the numbers are pretty close to what they say they are in terms of strength.
It was the test.
And this was the predicted failure. The predicted failure was like 620 pounds. And I think this is exactly 600 at this point.
See what you got now. Wow. It broke slow. It broke with.
Well, I can't show you, but I had a picture of, we just did the static test of the wing 2 months ago and took it to 7 Gs, 4,200 pounds, and I still have a wing. So I was happy that we did that scale model test before I actually designed the spar. All right, so that's an example of a scale model test. The next is ASTM testing. I've done a lot of this over the last couple of years. I kind of tried to follow Paolo's model of using students, and so I have done a summer internship the last 4 years where I have engineering students come and help me in the shop. I actually had one of Paolo's students from Brazil one summer, and then the rest have come from a lot from Cal Poly and a student from San Jose as well. I'll pass this around. This is the ASTM standard that I was talking about. You can just take a quick look at it if you want. But it's a super helpful guide to doing the kinds of testing that we do. And I'm going to be showing the results of some of the tests here. But these are coupons that we tested that looked at different face sheets. So they all have the same core. It's a Divinycell core. But then we changed out what kind of carbon fiber laminate was used with each coupon. The carbon fibers are all the same aerial weight. The only difference is the weave style. And they're all wet layup, but one of them is also pre-preg. So if you follow industry trade publications and this and that, the big recently spread toe fiber, where they take the toes of fiber and they spread them out into kind of flat ribbons. Spread toe fiber or non-crimped fabrics, like Paolo was talking about using a stitched fabric for his wing skins. The less up and down that the fabric has to do, theoretically, the stronger it is. I did not find that to be true. In fact, I found the opposite to be true, and I have a theory for that. But after the talk, you can come up and look at these if you want. These are the 9 different carbon fibers that I tested last summer with my students.
Is that bending, is it?
It's a flexural bending test, yep. And I've got a picture of it here in a moment.
What's that material? There seems to be 2 types of grades of carbon fiber. One is kind of a commercial grade and one is a military grade.
Yeah, pan and pitch, typically, yeah.
Are they all the same as one or the
No,
other?
there's so many different types of carbon, and a lot of it has to do with how they process it, and are you looking for strength, are you looking for modulus, and they can tweak those things.
So what did you,
Oh, what am I looking for?
what did you use?
So, I mean, I'm kind of learning as I go, and so maybe if I was to go back 3 or 4 years, I would probably I might make some different selections. But for most of this project, I've used straight XL 282, 284. It's the plain weave or twill weave that you can get from aircraft spruce. And for what I'm doing, it's fine. Again, this gets back to gauge factors. I use, a lot of the airplane is 2-core 2. And 2 is actually, that outer layer of 2 is kind of structurally more than you need, but you need it for handling purposes. Upper left, this is a picture of a bending test apparatus. You place the coupon right here. These pads rotate so that as the coupon flexes, it's not inducing too much lateral load on the coupon. This is a testing machine that I purchased because I realized that it's really hard to get time on testing machines, and so I thought, well, I'm really curious in this, I'll just buy it myself. And that was super expensive, and I thought, okay, well, I bought it, now I can do my testing. And then I looked at how much these things cost, and it costs more for the fixtures that you see in this picture than it would for the machine itself. So I made these myself and saved myself several tens of thousands of dollars. I didn't bring that. I have my compression tester if you want to take a look at that. This is for doing compression tests. This is a shear testing fixture. This is actually Paolo's dad built this, and Paolo gave it to me, and so I fixed it up. I actually haven't done any testing with it yet, but I promise I will. And then these are just some grips. These are super useful for just grabbing onto something and pulling. So for straight up tensile tests, I had a friend who was suspicious about some aircraft spruce bolts, and so we did some testing to validate whether the bolts were actually holding up, were exhibiting their spec performance or not.
Were they?
Yes, they were. Yep. They were probably, I think the problem was in the assembly and not the bolt itself. Okay, so I have been doing, I've probably done several hundred coupons of testing over the last 3 or 4 years, and I tried to assemble it into a little booklet. So this page basically shows the first set of tests that I did. I believe it was 2 or 3 years ago, and in that set of tests, it was the same type of coupons as these, but instead of varying the face sheets, I varied the core. So we kept the same face sheet for everything, and I varied the core. I looked at Divinicel 45, 60, 80, 100, and then Rohacell, IGF 51, 71, 110, and Honeycomb. And so I was trying to see, I just tried to learn what's the difference between these different foam cores. So this is a typical plot. You get a little bit of a curve here, and that's compliance. So the whole system is kind of settling in, and you get a little bit of force, but it's not linear. Then you have a linear region, and then at the very end, when it begins to fail, then it starts to go nonlinear, and then you have a failure. For all of these coupons, when we fabricate them and then when we test them, I write down all of the information of what we're doing. Some of it might be relevant, some of it not, but you just want to kind of keep tabs on all of your data in case you think that something might be important, and later you can go back and see. But what we're looking at is, one of the things I look at is fiber-resin ratio. So I'm always trying to shoot for about 60-40. Much higher than that, then I get a little bit concerned about dry spots, because this is all hand-laid wet layup. And then I also do a post-cure. So I'll talk a little bit more about post-curing later. But post-cure has a huge effect on materials performance. And then we're taking some data like the average load of all of the coupons, what that translates into in terms of stress, the strength, pounds per square inch, deflection, and then weight. And then coefficient of variance just indicates how similar one coupon is to another. And so this is also a good reflection of your manufacturing tolerances, or how good a person is, or how well are you manufacturing in terms of, is one part consistently made similar to another parts. And so having really tight or a small coefficient of variance indicates that you are achieving a certain amount of repeatability from one part to the next. So we tested all of those foam cores, and this is a summary of all of the different cores. So this is Divinycell 45, 50, 60, 80, and 100, and you can see as the density goes up, we get stronger, they achieve a higher and a higher load. Same with the IGF, 51, 71, 110, that's also going up. I don't know how familiar you are with Rohicell or Divinycell. Rohicell is a PVC foam. It's a little bit spongy. IGF, Rohicell is a polymethacrylamide, and it's kind of what you would call frangible. It's like a cookie, and it crumbles easily. It has higher mechanical properties, so you can see that if we compare, say, IGF 70, it's up about here, it's significantly higher than the Divinycell 80. So the Divinycell is a denser foam, but it doesn't perform as well as the Rohicell, because the Rohicell has better mechanical properties. The problem with the Rohicell is that because it's very frangible, any kind of an impact, you have a delam. And so I would never use Rohicell on an external structure like a wing skin. It's great for internal structures like spars or ribs, something that's not going to be suffer from delamination problems. But the Divinycell is, performs better for things that might be getting bumped around. Another interesting thing you can see is that when you get into the really lightweight grades of foam, you have a drop off in strength, and then it kind of plateaus. And so, between like H60 and H100, you get pretty similar results. So, and this is strength to weight, so it's just kind of an arbitrary, non-dimensionless measure of how strong these particular coupons were. But what it indicates is that you can kind of tailor the strength of your part by increasing the density of the foam, if that makes sense. Go ahead.
Is that the last one, the honeycomb?
Honeycomb is right here. And I'll get into why honeycomb is not as fantastic as you might think. Anyways, this was an interesting kind of thing to see in terms of having this plateau here and being able to get a little bit more strength by just increasing the density of the foam. Honeycomb is kind of a middle-of-the-pack performer, and the reason for this, at least from what I can understand in my study, is that when you're doing a really thin face sheet on honeycomb, and by thin face sheet I mean 1 or 2 layers of carbon, the space between those cells is large enough that you get dimbling, and basically you're getting buckling of the face sheet. So the foam works better for really light face sheets because it's a smooth, solid surface. And it also has micro buckling, but not to the same extent that honeycomb does. And one of the tests that I would like to do is to kind of look at where the crossover is, because it is well known that honeycomb is a superior core material, but you need to get past the point where you have micro buckling issues. And my guess is that you need about 3 layers of carbon in order to avoid the micro buckling in between the cells, if that makes sense. All right. So the next set of tests was looking at the different weaves, and again, that's the ones that we did right here. So here's just kind of bog standard aircraft spruce 282 plain weave carbon fiber, and just a very typical test profile there. And if we look at the overall results, starting on the left, this is 20 plane weave, so 20 is, 20 millimeters is the width of the spread toe. It kind of looks like a checkerboard. I don't know if you can see this very well, but it kind of has this checkerboard look to it, and it's about, it's 2 centimeters across. An 8 centimeter wide plane weave, an 8 centimeter wide twill, straight up 284, straight up 282, 284 prime text, which is I've got a nice picture of it here. So you can see that regular 282. If you hold it up to the sunlight, you'll see a lot of light coming through, because you have a lot of interstices here where the weave is not very tight. So one of Hexcel's new products is something called prime text. It's the same weave, it's the same toe, but they spread the toe a little bit out when they weave it, and so when you hold this up to the light, you see hardly anything coming through. So this is, again, kind of they're banking on the lower amount of crimp to increase the strength. I like this stuff because it handles really nicely, and I have wet wings, and so I wanted to have a really tight weave carbon fiber so that I wouldn't have to worry about leaking in the wing. So if we come back and look at these results, you'll see that the prime text was the best of the wet lay fabrics, and then the pre-preg, we also did a pre-preg. There's actually some pre-preg that I think Paolo used on, I don't know if you used it on your project or the X57, but yeah, it was X57 pre-preg, so they gave me some and I did a test. And it was by far the strongest, and it also, if you look at the error bars, not the error bars, the spread of the results, it's very tight. So I think that that's super cool, because that's indicating that no matter how good you are with, I mean, I've made a lot of these coupons. I think I do an okay job, but I cannot match pre-preg in terms of getting a consistent resin distribution, and that's what you're seeing right there. Because any kind of a failure that you get, that's because 1 or 2 fibers in that coupon did not have enough resin as the surrounding areas, and it cracked. And once it goes, everybody else around it goes as well. So this is a really tight spread, and what that means is that if you're designing a structure and you have a margin of safety, theoretically you could use a lower margin of safety for a pre-preg than you would for a wet lay. Or conversely, you would need to use a higher margin of safety for a hand-laid wet lay compared to a pre-preg. And so if you can use a lower safety margin on the pre-preg, you can have a lighter part.
Did you vacuum bag these?
Yeah, these are all vacuum bagged. Yeah, vacuum bagged at room temperature and then post-cured at 80 degrees Celsius for 4 hours, which is and it's MGS resin, which is, you guys are probably familiar with that because it's a glider resin. Next break, I'll just jump through the last ones really quick here. I wanted to, as I mentioned before, I have a wet wing, and so I was really curious about chemical resistance of various resins. And if you talk to the Long Easy people, there's a lot of folklore out there about which resin to use. Some people said that easy epoxy is the best, but you have to make sure and use the slow hardener. Other people said, oh, I just used Jeffco and it was fine. And since I don't believe anything, I just had to test it for myself. So I had a matrix of resins, chemicals, and post-cures. So I looked at MGS resin, Jeffco, and easy epoxy. I looked at room temperature cure, a 122, this should say F, not C, 122 degree Fahrenheit cure and 176 degree Fahrenheit cure. And then I exposed it to avgas, ethynylated motor gas, and then acetone. The reason I did the acetone was because I assumed that these would probably not have any appreciable effect over the 18 months of the test. But the acetone was a way of kind of speeding up, kind of doing like an acid test, as it were. And that would be these coupons. So if you come up and look later, you'll see that the room temperature cure and 122 degree cure, they're just basically little bits and pieces. But the one they get cured at 176 degrees is still basically a solid coupon. So post-curing has super duper effects on composites. And very quickly, I'm going to skip the last section of testing, which is testing of actual parts. But if you want to look, this is an engine mount bracket that you can look at later that got tested. This is a tail wheel bracket that got tested. And the last thing I'll talk about very quickly is those rudder cables that were going around. So this is steel, and again, very typical failure for what you would see for steel. You've got your linear region, and then you have it starting to fail here. And average load was about 1,900 pounds, and that's pretty much booked. Like if you look in the aircraft spruce catalog, they'll tell you that 1/8-inch steel is rated for something like 1,950 pounds, I think. I then looked at Dyneema, and I talked with a bunch of kite makers and different folks, and they recommended which Dyneemas to use. So I looked at something called SK78, and the first test that I did, this was it. And I was like, holy shit, this stuff stretches like crazy, I can't use it. So you've got a lot of compliance, and that's a lot of that compliance is in the splice and in the rope itself kind of getting taut. And then you finally reach this linear region, but that's after a lot of stretch. So what I realized that if you're going to use something like Dyneema for a control cable, you have to do a pre-stretch. And you do a pre-stretch to say 50% or 70% of your ultimate load that you plan to put on the cable. And then when you do that, you end up with much lower compliance. You basically remove all of that compliance, and you end up straight on your linear part of the curve. So the 1/8-inch Dyneema broke at 2,700 pounds.
Wow.
And always searching for the last ounce, I decided I would tone it down. So I got some 2.5 millimeter, which I believe it's close to like 3/32 of a brand new kind of Dyneema called SK99. And that fails at 2,100 pounds, and it saves me an ounce or something. So anyways, I will go ahead and close there because I'm going over time, but I'll take questions for a minute or two, and I don't want to run into the next person's speech. Yeah, go ahead.
Did you compare the sensitivity in terms of stiffness and strength of different thickness with the same core?
No, I did not. And measuring stiffness involves putting a strain gauge on something, and this is strain gauging flexural coupons is not really the way you want to do it. I did this just so that I could kind of learn about strain gauging composites. Yeah, go ahead.
Do you have a drawing or a photo of the actual aircraft design?
That's a good question.
We want to put a face to the numbers.
Right.
Aha.
Yeah.
Didn't Paolo do something like that?
Huh?
Never mind.
So that
No, Paolo says that if I break his record, he's going to break it back, but I know that he has bigger fish to fry.
and that's just for the C1A0 or 0 record. That's not for pylon racing or for any other.
Well, it'd be nice to have an afterlife as a Reno racer, but right now I'm just like trying to get it finished. So I'll think about Reno later. Yes.
Is the splice done manually on that?
Yeah, it's a manual splice, and it's a different splice than... I had to modify the splice, is something that I'll say. And I'm not going to go further than that because I'm not ready to say how I did that. But that's something where testing was super helpful because if I had just used a regular splice, it doesn't work.
And what about temperature changes?
Dyneema is stronger at lower temperatures than it is at room temperature. So it'd be great for a high altitude
does it expand or contract?
I don't, you know what, I can't answer that question. I don't think that there's a lot of expansion contraction as compared to steel, but don't quote me on that.
You mentioned about having some odd results with woven versus stitched
coupons. Could you expand on that, or you?
Well, just it was odd that the spread toe performed worse than straight up 282 or 284. And my theory on this, and it's just a thought, is that when you have really wide toes, they have a long stretch where they're going straight before they dip down and come back up again, right? So if you think of it as like an Euler column, the effective length is quite long. And they're not Euler columns, they're very different from that, but if all of these coupons fail in buckling. So my guess is that when you have a really tight weave, the effective column length of each fiber is quite short. I mean, it's the length of a toe. And so I think that may be what's going on. But in any event, what we tested, and this is another part of testing, is that when you make a test assembly, you often have 4 or 5 different parts of that assembly that could fail. If you look at this has a lot of bolts in it. I don't have bolts in the airplane. It's just a bonded assembly. But I didn't want this part of the test to fail. What I wanted to fail was this part right here. And so a lot of times, again, you set up a test so that you get it to fail where you want. And that box of cables going around, they all failed in the steel cable. So they failed like they were supposed to. And that'll be the last question, and then I'll be done.
Do you, with the dynamic cables, do you have to put spools or thimbles in the end, or how do you?
Yeah, you do need to have a radius at
And
the
you
end.
add that in the weight for calculation?
Yeah, well, on the Dyneema cables, they weigh 2.5 ounces, and 2 ounces of that is metal hardware.
Okay.
The Dyneema weighs nothing.
Okay.
Yeah. All right, I'm finished. Thank you guys so much for having me here.